Good morning, class. We are looking at Chapter 2, Section 2.1, Limits of Sequences, and this is being recorded. And it is up to you if you want to participate or not. If you want to turn off your audio, video, you can even change your name to your initials if it's a matter of privacy. So when I ask questions, you don't have to answer if you don't want to. All right, in Chapter 2, we cover limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits of algebraic methods. I'm going to also stop the video to make sure it doesn't get blurry. If it does, somebody can holler and we pause the recording until it becomes clear. So let's see what's going on here. First of all, let me also hide this floating. Recall we looked at sequences in section 1.6. A sequence basically is defined as a list of numbers starting from a sub 1, go all the way to a sub n, the general term. A recursive sequence is of the form a sub n plus 1, f of a sub n, which means the next term depends on knowing the previous one or previous ones. An example of that is a Fibonacci sequence that you add up previous sequences, okay, previous numbers, two numbers prior to what you have, okay? And so that's the idea for a recursive sequence. As far as arithmetic sequence, if you recall, we just add a constant, d, and recursively, a sub n plus 1 is the previous one plus d. Explicitly is a sub n equals a sub 1 plus n minus 1 times. In the case of a geometric sequence, a sub 1 times a common ratio r, and we keep on going to get to the general term. Recursively, a sub n plus 1 is the previous one, a sub n times r, and explicitly, a sub n is defined as a sub 1 r to the power of n minus 1. So I hope everybody's comfortable with that. This is what was discussed before, okay? And so now let's move on to the new stuff. So I'm going to give you the synopsis of what we are going to cover, and then we expand on that as we look at the concept as well as examples involving that. A sequence, as was mentioned, is an ordered list of numbers, okay? Limit, what do we mean by limit? The long-term behavior of a sequence. In other words, what happens to a sub n in a long term? So let's see how we are going to do this. The limit of a sub n as n approaches infinity is L. In other words, we can say when n approaches infinity, the answer is some number, any number. Then we say it converges. The sequence a sub n converges to L. But if it's infinity or negative infinity, or it doesn't exist, if it's somehow DNE stands for does not exist. Does not exist. DNE. For example, if it oscillates, then we say the sequence diverges. There is this concept of a limit loss, but we're going to simplify it into just plugging in and observing as to what happens. Now we're going to look at a couple of rules, okay? The limit as n approaches infinity, r to the power of n. If r is between 0 and 1, in fact, if r is between negative 1 and 1, if it's 1, it's 1, and if it's larger than 1, is infinity. Let me just change a couple of things here. Even if r is between negative 1 and 1 becomes 0. Justification for that, if you look at first large numbers, for example, if you have 2, and you square it, you get 4. If you cube it, you get 8. As you notice, when r is larger than 1, as I add to the exponent, it becomes larger and larger. And that's why this is the case. On the other hand, if it's between -1 and 1, for example, let's go with, let me use a different color here. Let's go with 1/2 and raise it to the power of 2. Becomes 1/4, and 1/4 is smaller than 1/2. 1/2 to the power of 1/3, it's even smaller, 1/8. And so that's the idea behind this theorem. So let me just write this. Does not exist here because I need that. Okay. Here's another theorem class, which basically says when n approaches infinity, and if p is larger than 0, what happens to this? This approaches infinity, and any number over infinity is 0. Even if that number is large, doesn't have to be 1. Even if it's 10 billion, it's still infinity. A number over infinity or a number over negative infinity is 0, okay? Any number, it doesn't matter how large it is. Now, here's the geometric sequence. The summation for a geometric sequence, we've seen this in college algebra, in pre-calculus. I have the proof here. Later on, you can look at it if you like. If the first term instead of a sub 1, we call it a, and the second one becomes a times r, and so on and so forth, we can show that s sub n, the first n terms, becomes a times 1 minus r to the power of n over 1 minus r. Okay. Now, speaking of this one that was infinity, I want to also write the following. When you have a number, any number, over infinity, the answer is 0. If you have any number over negative infinity, also the answer is 0, okay? All right, so having said that, when r is between -1 and 1, let's see what happens. When r is between -1 and 1, then this goes to 0 when n goes to infinity, and so you get a over 1 minus r. We also have this case, okay, so again, this is for geometric sequence. And by the way, b sub 0 is a depend on the text that you're using. So this is the geometric sequence. What if we start with adding a constant? This is like providing medication for patients. Okay, we'll see that later on when we look at examples of that. Then the solution for that is different, okay? And also I have the proof for that if you want to look at it towards the end, but we will discover this later on as we go through some examples involving that. All right, let's look at a few examples to make some sense out of what we just said, and let's expand on this summary that was explained, starting with a sub n equals 1 over n. We really are interested in finding the limits. And we, in essence, if you go back to the previous page, the theorem that I put up shows the answer. But let's calculate the first few terms. I hope you realize if I replace the n with 1, I get 1. If I replace it with 2, I get 1/2. If I replace it with 3, I get 1/3. In other words, the denominator is getting larger and larger, and the numerator doesn't change. It's fixed at any number. It doesn't even have to be 1. It is the denominator that is getting larger. Therefore, the fraction is approaching what? 0. So the limit of 1 over n as n approaches is 0, and we say it's convergent. Why is it convergent? Because we can pinpoint a number, everybody. we can pinpoint a number. If we were to graph it, it'll look something like that. And I hope you remember from, again, algebra, that if you were graphing a rational function, y equals 1 over x, it looked something like this. And we just have the right side because n is positive, okay? And of course, x is a continuous function, but n is discrete, so we have it at discrete values. That's why instead of a continuous curve, we have a bunch of points, okay, because it's discrete. All right, now, what about this one? If we replace the n with 1, we get negative 1 to the power of 1, which is negative 1. But if you change the n to 2, you get positive 1. In fact, you get negative 1 anytime n is odd, and you get positive 1 when n is even. So what does it mean? It doesn't settle down. Because the numbers change from one to another and they keep on changing, the limit does not exist, and it's divergent. So I want to make sure everybody understands what happens. When the limit is infinity, we say the limit is infinity and it's divergent. When it's negative infinity, we show it that it's negative infinity and it is still divergent. This one is oscillation. It oscillates between the two numbers. And if you were to graph it, it just oscillates up and down. And that's really the idea behind, for example, sinusoidal function is if you look at y equals sine x and you let x go to infinity, it oscillates between negative 1 and 1. It oscillates between the two, okay? So convergent means I can give you one number, end of the story, just one number. So a sequence has a limit and we write. So let's recap what we said in the summary, but with a little bit more finesse and details. We have a sequence, everybody, starting with a sub 1, a sub 2. And we write the limit is L. The limit of a sub n as n approaches infinity is L. L is some number, any number. If we can make a sub n fairly close, extremely close to L as n becomes huge, in that case, we say a sub n converges to L. On the other hand, if this limit, the limit of a sub n as n approaches infinity is infinity, that means we can make a sub n huge, okay, for a large n, then it approaches infinity. We also can write the limit of a sub n as n approaches infinity is negative infinity if we can make a sub n extremely, okay, negative infinity for all n being large. In both cases, both of these cases, infinity or negative infinity, the sequence diverges. In both cases, the sequence diverges, everybody. Okay. Now, we do have some limit laws, okay? And basically what it says, if we know that these two sequences converge, they are convergent, okay? And then when we add them up, we can separate them. When we subtract them, we can separate them. If there's a constant, C is some number, we can take it outside the limit. If we are multiplying them, we can separate them. If we are dividing them, we are separating them as long as the denominator doesn't go to 0. If we are raising it to a power, we can just calculate the limit of a sub n and then the result, raise it to a power. And the limit of a constant is simply constant. Those are some limit laws, okay? But as I mentioned, we take the easy way out, we simply plug in. Okay. This was also mentioned on the first page. This simply says what happens when the denominator is large. Now, one of the things I want to explain here, what happens if this is true when p is larger than 0, but if p is less than 0, because it comes up, it doesn't happen. What do I mean by that? I want to remind you of the following rule. A to the power of negative is 1 over a to the power of positive. Also, 1 over b to the power of minus n is b to the power of positive n. So what do we mean by that? Those are some negative exponential rules from algebra. I hope you remember that. The idea is that if p is positive, okay, so this is going to infinity, the denominator is getting larger, 1 over a large number is 0. But if p is negative, it really comes up, okay, so that's the idea. So that's why p larger than 0 is the key here. I can't emphasize this enough, okay? Now, we are going to look at this example, and this is a warm-up example, and let's refresh everybody's memory about this, which says the limit of r to the power of n as n approaches infinity depends on r. If r is between -1 and 1, this, if you remember, I wrote that for you, and I'm going to write it again. Not just 0 and 1, even between -1 and 1 will result in 0. If it's 1, gives you 1. If it's larger than 1, it gives you infinity. So what we do actually when it comes to taking the limit, I would just plug in everybody. So what happens when you plug in? I hope you realize if you plug in, you get 2 to the power of infinity minus 1 over 6 to the power of infinity, which is infinity over infinity. Now, I want to make sure everybody understands what's happening. Infinity times 2 is infinity. 2 to the power of infinity is infinity. Infinity times 10 is infinity. Infinity minus 1 is infinity. Infinity minus any number, even large, is still infinity. So you don't want to confuse that. But what is infinity over infinity? And that is important for everybody to know. We have a bunch of indeterminate. In concept of a limit, the following are considered indeterminate form: infinity minus infinity, 0 over 0, infinity over infinity, and there are a bunch more. Meaning what? You cannot assume infinity minus infinity is 0. It may be 0, or it may be some larger, or may even go to infinity. 0 over 0. Infinity over infinity, we have no idea what they are. We have to determine what they are. So when it says indeterminate forms, what does it mean? Here's my understanding of indeterminate form. To me, indeterminate form means more work. What do I mean by that? To me, it means use your algebraic techniques to figure out the answer. That's the meaning of indeterminate form. I'm going to tell you, in calculus, almost always we end up with indeterminate form. So infinity minus infinity, 0 over 0, infinity over infinity, and stuff like that. It is not done. You have to use your algebraic techniques to come up with the answer. And we may end up with 0, we may not, or a number, or infinity. So what is the technique? Let's cut this into 2 fractions. As you can see, this is one of them, and this is another one. So cut it into two fractions. What comes next? Well, this one is 2/6, which means 1/3 to the power of n. This one, even if you left it like that, class 6 to the power of n goes to infinity and 1/infinity is 0. But you can also write it 1/6 to the power of infinity and cut them into two pieces. Okay, so 1/3 to the power of n minus 1/6 to the power of n. So we are taking a limit of those. So this one minus this one. Now, when we go back to the top, everybody, we're going to use this one because R is what? Between 0 and 1, each case goes to 0, and the result is 0. Okay. So we plug in and we observe. So here's the next one, everybody. The limit of 2 to the power of n as n approaches infinity. So what do? We can go with that theorem or just plug in. What do I get if I plug in? I get 2 to the power of infinity. Am I correct, class? What is 2 to the power of infinity?
Infinity.
Done. Beautiful. Beautiful. Done. All right. We are going to do exactly the same thing with part B. We are going to plug in. So we get 5 plus 2 to the power of negative infinity. All we are doing, we just plug in. Class, what is 2 to the power of negative infinity?
It's the one where it's oscillating.
No. We can rewrite this with the exponential format that I mentioned, everybody. Remember the exponential format? This, we can write it as 1 over 2 to the power of infinity, which is 1/infinity, which is 0. And the answer is 5. Remember, the exponent is minus n, and the negative exponential rule, I'm going to write it again. A to the power of minus m is 1/a to the power of m. Okay. Example, 2, or let's say 3 to the power of negative 2, that means 1/3 squared, that means 1/9. This is an example. Okay. All right. What about part C? Let's plug in. Although, again, we can remember the, theorem that we know the limit of 1/n as n approaches infinity is, anybody remembers that?
0.
0, beautiful. Or just plug in. So what happens when you plug in is that 1/infinity, any number over infinity is 0. So 1 plus 0, and the answer is 1. Okay? All right. So we have dealt with this in college algebra and in pre-calculus when we were trying to find horizontal asymptotes. I hope you remember that. Basically, when you take a limit and n is approaching either infinity or negative infinity, the technique is to divide by highest degree term in the denominator, not the numerator. So we are going to divide by n squared, everybody. Everything gets divided by n squared. Why is that? Because if you plug in, you get infinity over infinity. So for a rational expression, when n is approaching infinity or negative infinity, the technique is to divide by the highest degree term in the denominator, namely n squared. Of course, division or multiplication by 1 over n squared, and here's what happens. I want to make sure everybody understands what happens. When you divide this one by n squared, you get 2. The second one, you get 3 over n. The third one minus 1 over n squared. When you divide the first one by n squared, you get 5. The second one, you get minus 1 over n. And the last one, you get 8 over n squared. So what happens? We are going to replace the n with infinity, which means you no longer write the limit, okay? The next step is not to write the limit. This goes to 0, this goes to 0, this goes to 0, this goes to 0, and the answer is 2 over 5. In other words, 2 plus 0 over 5 plus minus 0 plus 0, okay? What does it mean? As you can see, when the degree of the numerator and the denominator are identical, then the leading terms take over. And then their leading coefficients will give us the final result. I hope everybody remembers that. Okay, so we're going to continue with the same thing. We're going to divide, and remember, if you plug in, you get infinity over infinity. The technique is to divide by highest degree term in the denominator. So what do we divide this one by, class?
1 over n squared.
Very good. So we divide by n squared, meaning we multiply everything by 1 over n squared. That's the meaning of it. Perfect. When we do that, we are dividing everything by n squared, everybody. When we do that, this becomes 3 over n. This becomes minus 1 over n squared. This changes to 7. And this last one minus 3 over n. So we are dividing every piece by n. So what happens now? This goes to 0. This goes to 0. This is 7 minus this goes to 0. And the result is 0. I want to make sure everybody understands what happens here. This is extremely important to realize that we have 0 over some number. Of course, it happened to be 7. 0 over a number is 0, everybody, okay? But it's not 0 over 0. This is 0 over a number. So if we get 0 over any number, the answer is 0. If we get number, any number over 0, it's infinity, but the question is it negative or positive infinity? And I will show you how to arrive at the answer easily. So when we divide a number by 0, it blows up. But does it go to infinity or negative infinity? We have to figure it out. For part F, we are going to divide the top and the bottom by what, everybody? Highest degree term in the denominator is n. We are going to divide by n. We are going to divide by n, and we are going to write this. So this gives us n. N squared divided by n is n. This gives us 2 and minus 1 over n. Since n goes to infinity, this is 2, this is minus 0. Infinity over any number, it's infinity over 2. Infinity over any number ends up being infinity. The only thing I want you to be very careful is the sign. So here's my question to you in case we come up with the following, everybody. What is infinity, class, divided by, I'm making it up, minus 5? What is that equal to? Anybody? I couldn't hear you.
Infinity.
No.
Negative infinity?
Pay attention to the sign. So although it ultimately becomes infinity, but the sign, positive or negative, we're going to be very careful of. If you look at what we did here, the denominator was positive too. Positive over positive is positive. But this one, positive over negative is negative. So be very careful with the sign, everybody. Okay?
I have a quick question.
Yes.
Did you say we divide by the highest power of the denominator or the entire?
No, denominator. Just the denominator.
Got it.
So in this case, n squared. In this case, n. Completely different. I mean, ultimately, when the degree of the numerator is smaller than the degree of the denominator, we end up with 0. When the degree of the numerator is larger than the degree of the denominator, we end up with either infinity or negative infinity. But the highest degree term in the denominator. So let me use a different color here too. So we are dividing by n squared here. We are dividing by n here. Okay, everybody? Okay. We are interested in finding the first 8 terms and therefore finding the limit for this case where a sub 1 is given. And we have a recursive formula. A sub n plus 1 is 1 minus 1/3 a sub n. Whenever they ask you to find a few terms, as long as you show work for a few, you are in good shape. So for example, a sub 1 is given, and I want to find a sub 2, so I'm going to write the formula for a sub 2. So class, a sub 2 equals 1 minus what? Can anybody tell me? 1 minus?
1/3.
Continue.
A 2.
Okay, why don't we take a look at this one? A sub n plus 1 is 1 minus 1/3 a sub n. So if I want a sub 2 class, is 1 minus 1/3 a sub?
2.
A sub?
1.
1. Okay, class. Okay,
It's an n.
check this out. Is an n plus 1 larger than n by 1? So if I want a sub 2, 1 minus 1/3 a sub 1, I'm going to go down by 1. Do we understand this concept? A sub n plus 1 is 1 minus 1/3 the previous one. So when I want the next one, 1 minus 1/3 times the previous one. That's the idea. So I'm going to replace now in this formula a sub 1 with 2. 1/3 times 2 is 2/3. 1 minus 2/3 gives me 1/3. Everybody okay with this? Go ahead.
If it was a sub 3 is equal to 1 minus 1/3, would it be
Okay,
a?
hold on. Let me write it. Hold on. Okay, let me have it. Okay, a sub 3, go ahead.
Is equal to 1 minus 1/3 a sub 2.
Can I hear a hallelujah? You got it. All right. So that's it. It's very simple, class. And so now you're going to plug in, and instead of a sub 2, you are going to put the number you just came up with. Now 1/3 times 1/3 is 1/9. 1 minus 1/9 is 8/9. Let's just write one more. How would you write? Let me just grab a different color now. How would you write a sub 4? Let me hear you.
I got it. 1 minus 1/3 a sub 3.
Beautiful. And that's it. You are showing your reader that you understood what you need to do. You are showing step by step how to find a sub 2, a sub 3. Now you can use a calculator. I will explain this part at the end. For now, you can ignore that. And if you use a graphing calculator, and you can do that, it gives you this. Why am I giving you a chance to use a graphing calculator? Because this can get tedious, class, and that can get take a lot of time. If you have one question in your homework, is not too bad, but if it's more than that, it may take some time. So as long as you show a sub 2, class, again, let me just, a sub 2 and a sub 3, that's good enough. The rest of it, you can use a calculator. Now, I hope you realize the first column is telling us, okay, we are moving on, and we can go to the next one and the next one. And the second column is the result. So this is a sub 2, a sub 3, 4, 5, 6, 7, a sub 8. So if a sub 8 is that, and if it's not good enough, you can pick up a couple more. So I hope you see it appears that we are approaching 0.75. Okay. Again, you can use that to come up with the rest of them. It's easily. I'll show you in a moment using a calculator. But what if I want to prove this algebraically? So here's the algebraic proof. Assuming the limit exists as n approaches infinity, then limit for this, for the left and right, is the same. Okay, assuming the limit exists, look at this expression. The limit of the left side and the right side as n approaches infinity must be the same. Now, what if we are claiming the limit is L? Then we can replace this one with L and this one with L. So take a look at what happens. If the limit exists, class, the limit of the left side is L. 1 minus 1/3 L. The limit of the right side is also 1 minus 1/3 L. I hope you understand the algebra behind this. It's just purely algebraic what I'm doing here, class. So I'm going to repeat. Assuming the limit exists, this is the general form. The limit of the left is equal to the limit of the right. The limit of the left is L. The limit of the right is 1 minus 1/3 limit of a sub n, which is L. Now, if I move negative 1/3 to the left, becomes positive 1/3, and L becomes 4/3 L. Everybody can see, let me write that. Everybody can see from here, I can say, let me just put it up here. I can say L plus 1/3 L is equal to 1. And when you add these two, you get 4/3 L equals 1. Multiply both sides by 3/4. L becomes 3/4. I hope you realize 3/4 is the same as 0.75. I'm going to show you the calculator in a moment. Okay, how it's used. This one says a sub 1, whatever it is, a sub 1 happened to be 2, you store it in X. I've done that, so let's just quickly do that again. Let me just clear this. So number 2 is the first term. I'm going to store it in X. And then a sub n plus 1. 1 minus 1/3 X. So 1 minus 1/3 X. We are going to store it in X, and we're going to press enter. Notice what we get. We get the first number. Take a look at the first number. Now you press enter again. you get the second number. By the way, 0.333 is the same as 1/3, okay? And you enter, you get the next number, and you get the next number, and so forth. Why am I showing you this? Because this could take a little bit of a time, and I want you to save time, okay, class? As long as you show your work for the first two, then the rest is good enough. Let me look at the last page of today's lecture. I'm going to refresh your memory about what we have seen first, okay? Let me just hide the floating here. The arithmetic sequence, as you recall, basically we added a constant, you remember, d, and so recursively was a sub n plus 1 equals a sub n plus d. Explicitly was a sub n equals a sub 1 plus n minus 1 times d. An example of that, we are adding 4, right, class? A geometric sequence, a sub 1 times r, and then times r squared, and so forth. Recursively, a term is the previous one times r, and explicitly a sub n is a sub 1, r to the power of n minus 1. An example, 1 times 4, 4 times 4, so on and so forth. Now, we will discuss this later on that. We have seen this in algebra, of course. The summation, if we want to add the first n terms, and assuming we call the first one a instead of a sub 1, we can show that this would be the sum. This would be the sum. The sum of the first n terms is a times 1 minus r to the power of n over 1 minus r. What happens if r is between -1 and 1? If this is the case, then this goes to 0, and we get s sub n equals a over 1 minus r. We take it from here next time.